Hi and welcome! In this module, we will learn how to construct a fixed dome anaerobic digester. We will run you through this process in 8 steps: calculating the dimensions of the dome, digging the hole, setting the conical slab foundation, building the dome, ensuring air and water tightness, constructing the inlet, constructing the outlet, and backfilling with soil. We will show the case of a digester built by Borda in Dar es Salaam, Tanzania. Borda stands for Bremen Overseas Research and Development Association, and it's a German non-governmental organization working, among many other things, on sanitation. In this module, we will connect with Gottlob Ngoda, who is the head of design at Borda Tanzania. Hey Gottlob, I heard you recently constructed a new digester. Please tell us about it.
Hi Manuel. Sure. The fixed dome digester shown in this module was built to accommodate and treat 10 cubic meters of fecal sludge per day, saving approximately 40,000 people. Nevertheless, such reactor could also accommodate and treat kitchen and food waste with minor changes in the design. The digester has a volume of 50 cubic meters with a diameter of 6 meters and a total internal height of 3.85 meters.
Thanks! For those listening to the module, remember that wet mesophilic fixed dome digesters operate in continuous mode as shown in a previous module. We distinguish 4 main important elements: the inlet, where the material comes in, the outlet, where the digestate leaves the digester, the dome, and the gas outlet. Now, let's see how they built each of these components. Let's start with the dome. The very first step is to calculate the dimensions of your digester. An example of this calculation is provided in the module entitled Calculating the Size of an Anaerobic Reactor. We recommend you to watch that module to learn about the calculations required. Once we know the digester's dimensions, we need to decide where to locate the digester. Most of the fixed dome digesters are located underground to save space and protect the digester from temperature changes. Of course, this implies digging a big hole. Ideally, such a hole is dug by machines. Otherwise, make sure that you select a location where the ground permits manual digging. Here we see operators manually finalizing the hole. And here we have the finalized hole. Hey Gottlob, please, tell us how big this hole was.
Yes, the hole was around 4 meters deep and had a diameter of 7 meters, which is obviously bigger than the 6 meters diameter of the planned digester.
Thank you, Gottlob. Once the hole is ready, the third step is to prepare the foundation for the digester. In this case, the foundation of the digester has a slight slope towards the center. That's why it is called conical foundation. Let's hear from Gottlob how the foundation was built.
First, the center of the surface needs to be identified, where you can locate a vertical metal bar. Then, lay some stones and distribute them uniformly on the entire surface, already giving the right inclination toward the center. This can be done using a radio stick as shown in the picture. Next, pour a liquid mortar onto these stones, making sure that all pores and cavities are filled. Flatten the surface. Then, add metal meshes to reinforce the surface, adding an additional layer of concrete afterwards.
Great! Once the floor is ready, it's time to construct the dome of the digester. These are the materials you need for building the dome. Bricks, concrete bricks or clay bricks, around 4,000 to 4,300. Cement mortar, about 6.5 tons. 130 kilograms of waterproof cement. 20 cubic meters of sand. Hooks to hang the bricks. You will understand this in a minute. The same radius stick as you used in building the slab foundation, or a string of the length of the radius of the dome. Gottlob, please, tell us now the steps followed to construct the dome.
You can start by laying the first layer of bricks using the radius stick. Pay attention to the edges of the bricks to make sure they match well between each other, and make sure that mortar is added in all joints of the bricks, making the dome airtight. Layer after layer, continue adding bricks with ever-increasing tilt to the center. The cement mortar forms a strong bond with the bricks after a few seconds. The secret to the building of a dome is to hold the bricks in place with special hooks until the mortar dries a little, or until the layer is complete, as shown here. Here we also see the element which will function as inlet of the feedstock. These layers of self-supporting bricks placed on top of one another enable to build the dome as freestanding without using any sort of frame. In this movie, we see the dome almost finished. The operators are adding a mesh externally to the reactor in order to avoid any alteration of the shape. Here we see the finalized dome, which has been plastered. Check how the gas outlet pops up in the middle of the dome. The outlet can be connected to a stove or a generator.
Once the dome is finished, the next step is to ensure the air and water tightness of the reactor. It is important to mention that the main problems that these sort of digesters present are related to the gas tightness of the brickwork or the cracks causing heavy losses of biogas. Fixed dome digesters are, therefore, recommended only where experienced biogas technicians can supervise their construction. The volume of the dome above the lintel is where the gas will be stored until it is consumed. It is therefore crucial to make the inner wall of the dome in this section completely airtight. In the case of Dar es Salaam, this is done by applying 7 layers of plaster with waterproof additives. Before putting the plant into operation, it is highly recommended to conduct gas pressure and water tightness tests. The next step is to construct the inlet. Here we see how the inlet of the digester was built using the same procedure as shown for the digester. Bricks are stuck to each other using mortar, a mesh, and a plaster on top. Depending on the feedstocks to be digested, we distinguish 3 types of inlets. Normal inlet chambers for all sorts of chopped biowaste. Here we see some examples. They often required manual filling and steering as shown here. Then we also have sanitation interfaces, toilets, etc. Often biogas digesters are directly connected to private or public toilets with an additional access point for other organic materials. And settling tanks, used for feedstocks with high liquid content. Here the effluent is separated from the sludge, bringing only the sludge into the digester. This is the case for the plant in Dar es Salaam. If you want to learn more about settling tanks, have a look to the Compendium of Sanitation Systems and Technologies. Let's now mention 3 construction hints. First, always make sure the inlet is higher than the outlet. When gas is produced, the slurry is pushed both ways towards the inlet and the outlet. Therefore, it is absolutely crucial that the outlet level is lower than the inlet level to avoid the slurry being pushed out through the inlet. 10 or 15 centimeters of height difference are normally enough. So if this is not the case in your system, you want to look for ways to lower the outlet, or if not possible, to raise the inlet. Other aspects that could be added to the inlets are a closing lid to avoid mosquitoes or other pests from breeding in the digester, and a mesh to avoid particles bigger than a given size from entering into the digester. Godlove, now that we have learned about the inlet, could you tell us something about the outlet?
The outlet of this digester consisted of an expansion chamber. This serves to collect the digestate. Finally, this digestate can either be discharged into a centralized sewer system or further treated to eliminate pathogens and organic loads before discharging it into the environment or directly used in agriculture, ideally with fruits, trees, or vegetables whose eatable part is far from the soil.
Besides the digestate that comes out through the outlet, after a while a heavy sludge tends to accumulate at the bottom of the digester. A common approach to remove this sludge is to install a desludging pipe such as the one shown in this illustration. In the case of this reactor, it is planned to be dislodged once every 4 months. EAVAC's Compendium of Sanitation Systems and Technologies gathers many other treatment technologies that could be used to treat and reuse this digestate. You can find the link to the compendium in this week's reading list. The very last step of the construction is to backfill the gap between the digester and the ground with soil as shown in the picture. And this is it. So, in this module, we went through the construction steps of a fixed-dome anaerobic digester. Thank you very much, Godlove and Borda, for joining us in this module. For those of you who would like to get further inputs on the topic, we recommend you the following key literature.